Hello, I'm Gray, the chassis lead for the UBC Motorsports uh, team this year, and I'm gonna host this little NX Nights video um, to show something that I thought was really cool. I think you guys really like. It might come in handy for some of your designs. So start off. Let's say we want to design a water pistol nozzle. So that pistol has some inlet diameter. It comes down, it'll have some outlet diameter where a certain pressure within the water gun, with like water traveling at a certain speed, will flow through the nozzle and exit into the air and then splash somebody. It'll be so who knows how long. And we want to design this. So we want to soak, let's say we get from like a manufacturer says, hey, we want to soak children with this much like volume flow rate of water, so 0.1 meters cubed per second. We want the nozzle to be lime green. We want kids to use it primarily in fields, so this will come in handy later. We don't want the nozzle to break easily, and we want it to be about 3 inches long. So we can find some things that we can't change regarding this situation. So the atmospheric pressure will always be this many pascals. Density of water will have this value here. And then just to show what units we're doing, measurements will be in millimeters. And velocities will be in meters per second. Things we can control. So all these values, I should probably say, is coming from the Bernoulli's equation, which is a flow rate equation. For those who are initiated, this should be very familiar to you. You've probably worked with this a lot. For those who haven't, it basically says that with a pressure, height difference, and then like densities or whatever, you can, at one end, you could figure them out on the other. So how velocities or pressures change by going through different cross sections. Anyway, from here we can find that like different values we can control. So let's say this water gun will make 80 times like 80 atmospheric pressure inside of it. Its inlet will be 2 inches. It'll have this much volume flow rate. I threw some numbers on here. Wall thickness, let's make it a mil. Should be okay. We'll see if it breaks later. And then distance, this should actually be closer to 3 inches, but whatever. We'll leave it at 30 for now. And then substituting all of these values into the Bernoulli equation, you get something like this. Is what it would look like instead. Instead of like P1 and V1, you'd have atmospheric and splash. So this is the exit. So exit is equal to inlet. So because we're in a field, we're not going to have a height difference because technically speaking, this inlet and the exit will be on the same height level, so gravity won't be in effect. So we can just neglect those two terms. And we'll only be focusing on the pressure on either end and then velocities. This equation and this example was inspired by this Khan Academy link called Finding Flow Rate from Bernoulli Equations. I chose this example, and you'll see in a bit here what this has to do with NX. But yeah, hang with me here. So we want to soak our friends with this much water per second. So we can find the volume flow rate by taking the area times the velocities at that cross section. In other words, the velocities are equal to the flow rate over area. So here we can calculate it. What our areas would be given a diameter. So this is what it comes out to. Pretty straightforward, I think. This is at the up here. Right, so we have diameter 1 is a diameter. We find the area of that. using the area and then the flow rate that's specified here, we can find the velocities of the water gun on the inside. That'll help us solve for this. And PWG is just a version of 80 times our atmospheric pressure. So this is just math stuff. The math stuff doesn't really matter as much as what I'm going to show you next, but I'm just kind of going to blow through this. From this, if you plug all these values in, what we're looking for is V splash, or the velocity at the exit of this nozzle. From this, we can use that velocity to find the area and then eventually the second diameter, like how big does this nozzle have to be in order for this all to work. We find that the velocity is this much from a nice equation, which is Bernoulli, just summarized up here. You can pause and take a look at it if you want. From there, stick it into this equation, we find the area is this much, and then converting it to diameters, we find that's how much in millimeters, or has a radius of 0.0624 inches. This has been converted to inches up here because my NX is set up in inches. So with these values, we find that the radius, which we specified, so this is 2-inch diameter, so 1-inch radius at the top or at the inlet. Second radius, or the exit, would be that much. Thickness converted, and then distance, or how long it is, taken from here, converted to inches as well. So we can use this right here, or these values, and I'm showing this like this is an example, but if you had some kind of work that you're doing that requires equations to determine certain parameters of your model, and you have results like this that determine what your model is going to look like, you can use those in NX. So we know that this is what we want our NX model to be. So if I go to NX, I can do a quick sketch here. Go into the right plane. We'll do a side view of the nozzle here. Let's make something like that for now. I'll specify some arcs, which might look a little bit weird at the moment, but just trust me. There we go. Let's say, this would be the inlet, let's say. Let's make this side the inlet. So if you go there, we said the inlet was going to be radius of 1 inch. So let's say 1 inch radius. Whoa. Okay, 1 second. Okay, I think there was something up with how I defined it there, so I just deleted it and redid it again. So we'll set this as 1, let's say. Let's make this piece vertical. This will be the inlet, so this is the exit. This is the inlet. Inlet we said was going to be, ooh, actually that's the wrong way around, isn't it? This should be 1. I'll just scale it down. Then the exit should be radius 2, or 0.06. I was doing this about, so just hang with me. This, we'll just shrink it down. We'll make that, you know what, let's make it like, yeah, 0.25 is okay. Make this like, I don't know, 0.3. Why not? I'm just kind of assigning some arbitrary values here for now. We'll go make those arcs again. So we'll not define these with actual values, we'll just assign them with relations. So if I set these two to be tangent, allow it to change the curves. I'll assign these ones to be tangent. They already are, but we'll do it again. And then the actual two radii themselves, it looks like they're tangent already. Oops, I think I clicked the wrong thing, maybe that's why. Yeah, it's not tangent, so it's close, but it's not quite. So we'll make a tangent. And that way when we adjust this later on, I'll show you in a second here, these will be able to move freely. Let's set this distance, which was distance L. So I said distance L is 1.18. So let's do that then. 1.18. We notice here that these black lines are defined and the yellow ones are not. So the yellow ones can move freely, and that's okay. We'll let them do so. So I'll save, or I'll finish this. It's really small. I'll save it. We'll do a revolve feature. So curve is already highlighted. We'll specify what vector we want to revolve around. So I'll choose the y-axis. And I'll hit OK. We got something that kind of looks like a nozzle. Actually, I kind of want to go back in here. I want to go like this. Move. Yeah. Make you 0.3. Okay, I think that'd be okay for later. But let's say you have a nozzle like this. And let's make it a shell. So I'll go ahead and click it. We'll make the thickness 0.1 inch. Let's say. Flip it around the other way around, so on the outside. So if I make this bigger, the outside will grow. If I do something like much larger, it'll see it better maybe. Yeah, so the outside will grow, but the inside will stay the same, which is what we want, so that those flow equations will stay the same on the inside. So let's keep those back to 0.1. It's a good thickness. We'll apply that. And then on the outside here, I want to make a hole that goes through so we can actually use this nozzle. So I'll do an extrude on that face. I'll make a circle. And I want to grab this edge. If you don't see it highlight, you have to go here and hit entire assembly. So we'll go entire assembly, we'll click the edge. It's fully defined because it matches up with this reference circle. We'll finish it. We want to extrude it in the opposite direction, so we'll flip it around. And instead of doing a value, let's just do until selected. So let's select this face. And that way, instead of it just having a hole that goes all the way out, it could have some weird properties. Let's say if this length gets longer than 2 inches, then that hole won't disappear. We'll still have it because it'll be stuck to this face. It will always be there. So let's go ahead and apply that, and now we have our hole that goes through. So there is our nozzle. Now, we send this off to the water gun people, and they come back to us and they say, hey, a child can't output 80 times the atmospheric pressure in a water gun. They can do more like 3. The diameter is way too big. Our diameter for like the tube we use is 1 inch. The wall thickness is too thin. It breaks too easily. So I need it to be thicker. And then the distance, 30 is a weird number. It's easier for molds are all in imperial, like easy imperial values. So that has to be 1 inch as well. Or let's do 2 inches. Let's do 2 inches. All these values change, and so do our radiuses and thicknesses and whatever. Instead of grabbing these and then going back into here and then updating the sketch and signing this off, there's a better way to automate this, which is, I'm sorry it took 15 minutes to get here, but this is where the fun begins basically. So if I save this, these new values are now saved here. I go in NX. I'll open up the sketch and I say, all right, I want this right here. If you double click it, you double click your dimension, then right click, you can add or remove an expression. So there's no expressions on this, so when I click it, it'll add an expression. Upon adding the expression, you'll get something like this with a drop down menu. In the drop down menu, you can hit function, and in function you can choose spreadsheet. So what this allows us to do is reference a spreadsheet so that when we update the spreadsheet, we'll update the model. So we can choose Excel read, we'll read a number. We'll choose our spreadsheet. I stuck it here. I'll specify the cell that it's in. So the value I want, so this is the inlet. So that'd be diameter A, or diameter 1, sorry. So that'd be radius 1. So radius 1 is in C3. So we go back here. We choose C3, we hit enter, or we can just click the screen, just left click the screen. So it already updates, so that's good. We can go here, I will double click, right click, add remove expression, hit the drop down, function, scroll down to spreadsheet, do the number read, hit OK. We'll grab that Excel file again. This is the exit, so we're looking for radius 2. Radius 2 is C4. So we can go back here, hit C4. And we'll click the screen once. It'll take a second to update. I'll leave these for now, as well as this one. This is the length here. So let's double click, right click, hit the drop down, go to function, choose a category. So we'll go back down to spreadsheet, number, choose the spreadsheet, and then select the cell. So the length is distance L, C6, C6. Go here. And we'll click. Oh, much longer already. It's went from 30 mil to 50 mil, so that looks about right. And there's one more thing we can change, and that is the thickness. So let's go ahead and finish this sketch because the thickness is in the shell. So in all of these, like shell and extrude stuff, the drop-down menu is available. You've probably never clicked it before because you never had a reason to, but it is there. If you click it, you get the same things. So if I go function, spreadsheet, number, choose the spreadsheet, and then I think it was C5, wasn't it? Yeah, thickness C5. Okay, accept it, and there we go. There's our new nozzle. We can save that. Now let's say that we start sending this nozzle out to multiple manufacturers, and all these manufacturers come back to us with all kinds of crazy changes they want made to this nozzle. So they change it again. They make this thing 100 mils long. They make it only 20 mil tall. The thickness goes down to 0.5 because they're using, like, I don't know, metal or something this time. They can output out to like 100 atmosphere. So the values change dramatically, as you can see here. All we have to do is save the Excel sheet. So after you did all your new calculations and such, you can save your Excel sheet with the new values in place. And in NX, all you have to do is go to Menu, up here in the top corner, Tools, Update, then Update for External Change. So you can see menu, tools, update for external change. Upon doing this, it updates. And now I have a really nice long nozzle. So why does this matter? Let's say you're in some kind of nozzle making business or any other kind of business that makes some kind of part, which companies want to buy from you and they want to change it. They'll come to you and say, hey, I want this to be different. I want this to be like whatever sizes or whatever. Now you're capable of making adjustments on the fly based on whatever values you're looking for, basically. So the manufacturer comes up to you, or the company comes up to you, says, I want a nozzle that has a flow rate much higher than this, of different values. Shape, what's called the shape A of a nozzle. I want you to make it for me. I want you to make it for me quick. Instead of doing all these all this work again, and then modeling it, and then being exact with all these values, you can just change the values that they want. It'll spit out the dimensions of your component, and then you just update it, and you now have a component that will be to that company's specifics. So there's probably a lot more ways you could use this. If you ever need to do calculations or something, especially a lot of iterative calculations for your work, you could stick it in Excel and then have it chug out a bunch of values, and then just have NX update through them. And then you can do analyses on them. So let's say you want to do some kind of flow analysis on a shape like this. You could have your equations that set up flow, what values you want to change. That will spit out some kind of relation to the dimensions of your component. And it's just as simple as saving it and updating it, which will come in handy, especially for more difficult components that don't only, like this one has a few more things, right, that we just defined to keep it fully defined. If you had something with so many more values and you're like, oh my goodness, what do I change? What you can do is you can optimize a component for a specified whatever. So yeah, something cool. So now you can link Excel files to NX, and you can use Excel files to manipulate your components and your parts. Thank you.